Glycosides are derivatives of hemiacetals, and here we have an alpha glycoside. And notice we have a full acetyl structure now with glycosidic linkage, but it's no longer OH, there's an organic group. R is just a random organic group in chemistry. Glycosides are less reactive than the corresponding monosaccharides. The derived methyl isomers will not undergo mutarotation. So here we have methyl alpha D glucopyranoside, and that gets locked into place now. And here we have beta. D-ribose and its derivative D2-deoxyribose. D-ribose is essential in RNA, deoxyribose is essential in DNA, and deoxyribose is produced from ribose in a chemical reaction. The 2-deoxyribose indicates that it's that carbon number 2 where the OH was replaced with an H. Deoxy means you're missing an oxygen. Ribulose is a ketose related to ribose. It is a biological intermediate used by cells to make other monosaccharides. So write the abbreviated Hawthorne formula for beta-D-ribofuranose. Well, we have beta. We know the OH is going to be up because it's beta. D, we know that in the Fisher projection, the OH is on the right. In furanose, it's making a 5-membered ring. Disaccharides. Carbohydrates consisting of 2 monosaccharide units. 2 monosaccharides connected by a glycosidic linkage are a disaccharide. And if you hydrolyze them, you get your 2 monosaccharides back. So lactose. Here we have a D-glucose and a galactose. Maltose is not found in the free state. It is a product when a polysaccharide is degraded during the sprouting of grain. So malting something. Hydrolysis in the presence of acid or maltase will produce 2 molecules of glucose. So maltose is 2 monosaccharides of glucose bound together. So here we see 2 glucoses coming together to form a maltose. And this specifically happens when you're sprouting grain. Purposely malt it. Sucrose and lactose are important disaccharides found in the free state in nature. Sucrose is known as table sugar. Lactose is known as milk sugar. Both undergo hydrolysis in the presence of an acid or an enzyme, sucrase or lactase, to produce. Sucrose is broken back down into glucose and fructose. Lactose is broken back down into galactose and glucose. Because in sucrose, both anomeric carbons are bound together, it's a non-reducing sugar. It's actually one of the most stable disaccharide, which is why so many plants can produce sucrose, because it's the most stable way to hold energy in a disaccharide. And so sucrose is the best disaccharide storage tool, and so many different plants produce sucrose. And so there are sugar beets, there's sugar cane, there's lots of different plants that have the ability to really upregulate how much sucrose they're producing. Lactose consists of a beta-D-galactopyranose unit linked to an alpha-D-glucopyranose unit. So we have a galactose and a glucose producing lactose, which is milk sugar. And notice the bond can be alpha, like in maltose. You have an alpha bond. This one, they're both going down. Or we can have a beta bond, where one going up and one's going down. So that's a beta linkage as opposed to an alpha linkage. Which is important because that's what's going to determine the difference between starch and cellulose. One has alpha linkage, one has beta linkage. So sucrose is a glucose and a fructose. And it is an alpha linkage. Alpha 1,2 glycosidic linkage. Because it's an alpha linkage between carbon 1 and carbon 2. So draw a disaccharide formed from 2 alpha-D-glucopyranoses with an alpha 1,4 glycosidic linkage. Again, the important thing with the alpha linkage is they're both down. In a beta, one is up, one's down. Sucrose represents 40 to 60% of all sweeteners and is 20 to 30% of the average caloric intake in the United States. And as people are eating about 2,000 calories, a lot of people are getting up to 700 calories a day from sucrose. And it is first hydrolyzed to glucose and fructose, then fructose is isomerized to glucose, and it all goes through glycolysis and gets broken down to pyruvate. The pyruvate, if oxygen is available, a carboxyl group will get ripped off and you'll form acetyl-CoA, and then it'll enter the citric acid cycle and completely get broken down to carbon dioxide, which is what you will breathe out. Sucrose is hydrolyzed to glucose and fructose to prevent crystallization and is called invert sugar, and invertase is used to break it down. A good example of this is the cherries they sell at Christmas. You have a cherry and you put solid table sugar around it and then you chocolate coat that, and then with a needle you insert the enzyme that will break down the solid table sugar into a liquidy mixture of glucose and fructose. Then you heat the chocolate a little bit to seal the hole that the needle went through, and now you have your chocolate covered Christmas cherry because it's fully chocolate covered, and inside you have a cherry in a very sweet liquidy solution. And so if you ever look at the ingredients for those chocolate cherries, you'll see invertase, which is the enzyme which breaks sucrose into glucose and fructose. Artificial sweeteners was developed with the intent to balance concerns for safety, sweetness, and aftertaste. Basically, people want to drink sweet things, but they don't want the calories from drinking sweet things. And we've developed sacharins, aspartames, and sucraloses. There are pros and cons of that. On the plus side, the original artificial sweeteners were meant for individuals who are diabetic, who would serious effects if they drank a sugared pop. And so our first one was Tab, and it was literally for diabetic people. However, companies saw the marketing potential of a zero-calorie soda, and so they named it diet soda. But there's no evidence whatsoever that says it helps anyone diet. Because even though you're replacing a lot of calories out of your diet, artificial sweeteners typically act as endocrine disruptors, and they mess up people's hormonal balances. And so the general effect that we see with artificial sweeteners is actually a lot of weight gain. And that's just not in people, that's in lab animals too. And so it's counterintuitive, because if you switch from sugared pop to artificial sweetener, you would chop out a huge amount of calories from your diet. And so you'd intuitively think it would lead to a lot of weight loss, but in practice that doesn't happen because it's messing with people's endocrine systems and their hormonal systems. Alright, the relative sweetness. Again, fructose is the sweetest sugar with 100% sweetness. Then we have invert sugar, which was sucrose that's been broken down into fructose and glucoses. Then we have sucrose, table sugar, then glucose, and then maltose, galactose, and lactose, which are not very sweet. The sugar substitutes, look at how sweet they are though. They're super sweet. Sucralose, that is, if we move it out 4, that's 35,000. So it is, and then if fructose is 100 and sucralose is 35,000, it's 350 times sweeter. And so sucralose is 350 times sweeter than fructose. And that's why if you see an experiment on Facebook when they boil away a diet pop, there's almost nothing left. If you open up a bag of artificial sweetener to pour in your coffee at a restaurant, only a little bit of that powder is actually artificial sweetener. The rest of it's just filler, because if you just had the artificial sweetener, it would be too small of an amount for a person to effectively and satisfactorily use in their coffee. Because again, these artificial sweeteners are hundreds of times sweeter than sugar, so you actually use a lot less. We have saccharin, which is also called Sweet and Low. Sucralose is called Splenda. Acesulfame potassium, Sweet 1. Aspartame, Equal or NutraSweet. Rebiana, which is Truvia, and Neotame. So there's a lot of sugar substitutes out there that are all hundreds of times sweeter than sugar. and so you don't actually need to use that much of it, which is why if you boil down sugared pop, you end up with a syrup. There's a lot of sugar in there. With the sugar-free pop, there's almost nothing left because it takes much less sweetener to give the desired sweetness. Redox chemistry of carbohydrates. This is fundamental to life. Almost all cells derive energy from oxidizing glucose through glycolysis in the citric acid cycle, and then oxidative phosphorylation to produce the ATP that the cell needs to survive. So the energy yield from the oxidation of glucose is shown below. 1 glucose plus 6 oxygens is broken down into 6 carbon dioxide, 6 waters, and 2,820 kilojoules of energy. And if you take a biology class or a biochemistry class, they'll go more into these steps of glycolysis and the citric acid cycle, and then the electron transport chain of the mitochondria, which then finally allows you to produce ATP and use that energy in biological reactions. Oxidation. The aldehyde group in monosaccharides can be oxidized to a monocarboxylic acid. And that takes a very weak oxidizing agent because aldehydes are super reactive, so it does not take much to oxidize one to a carboxylic acid. A little bit of bromine in water will do the trick. And here we see a little warm dilute nitric acid, and we oxidize the aldehyde very easily. And here, because this is a little bit stronger than just the bromine in water, we get a dicarboxylic acid. Notice the bottom. The bottom alcohol is also oxidized. Whereas here, with the bromine in water, you only oxidize the aldehyde moiety. With the warm dilute nitric acid, we oxidize both groups, the aldehyde and the primary alcohol, to get a dicarboxylic acid, which is synthetically useful in chemistry. Reduction. Hexahydric alcohols containing 6 OH groups are formed when aldohexoses are treated with reducing agents. And so here, hydrogen and platinum gas will reduce an aldehyde group to an alcohol. So we get the sugar alcohols like sorbitol. These are really bad for dogs. Never let a dog get molecules like this because they can't break them down like a person can. Reducing sugars. They'll reduce silver ions to free silver. It's a common test for an aldehyde group. Or you can reduce copper 2 ions to copper 1 ions. So again, the Tollens test, you have silver nitrate and it gets reduced to metallic silver, and they do this experiment a lot because the silver will precipitate on the glass of the beaker, making a nice silvered mirror, or you can make Christmas ornaments if you have a glass sphere like that. In the Benedict, Barfod, and Filling tests, copper 2+ is reduced to copper 1+, giving a color change from the bluish of copper 2+ to the brick reddish of copper 1+. And so again, it's a visual reaction. Sugars with the hemiacetal structure can be reduced under alkaline conditions because the ring opens as shown below, forming an aldehyde group. So the rings, the hemiacetal portion can open up, and then it can be attacked. Sucrose, however, is not a reducing sugar because it does not have the hemiacetal structure. So if we see sucrose, well, they don't show us the picture right then and there, but with sucrose, the 2 anomeric carbons are bound to each other. Notice with glucose, you have that OH there. With maltose, you have that OH there. And that makes it a reducing sugar. It's active. It'll react with these tests for carbohydrates. Whereas sucrose will never react in this test because it's a non-reducing sugar. It doesn't have a free chemical moiety for the reduction. Alright, draw the product's form when D-ribose reacts with bromine in water. Again, you're going to oxidize the aldehyde group, but it's not strong enough to oxidize the primary alcohol group, giving you the carboxylic acid. But the bottom primary alcohol stays the same. Major polysaccharides derived from glucose. We get cellulose, which is what we make wood out of, and there's cell walls in plants. Glycogen, the energy storage of glucose in animal livers and muscle tissues. And starch, the energy storage in plants. So cellulose is structural for structural purposes. Starch is energy fuel for energy purposes, and so is glycogen. And they can be broken down to glucose if necessary. So starch, it's a polysaccharide found in plants composed of amyloses and amylopectins. Amylose is a large molecule consisting of unbranched chains of 25 to 1300 glucose units. And these are alpha linkages. Fuels typically have alpha linkages because they're easy to break down. All organisms have the enzymes to break down the alpha linkage. Amylopectin, again, is branched now, but still has the alpha bonds, alpha 1,4, alpha 1,6. And so here we see the structure of amylose, which makes up plant starches. Amylopectins are branched, but again, they're alpha linkages. They're food. And so starch has alpha linkages. It's a good food source in plants. It's not soluble in cold water due to its super large size, so it forms a colloidal dispersion. And it'll bind up iodine to give a blue-black color, which is the positive test for carbohydrates, or specifically starches, because iodine fits perfectly into this pocket here. Iodine will fit in here perfectly, and all the water gets excluded, so you get that beautiful purple bluish iodine color back. And so iodine is a useful indicator. Glycogen is the carbohydrate polymer that is stored in animal livers. And glycogen is also stored in animal muscles, which you have a huge supply in the liver. And the liver is the one place that can free it and purposely put it into your blood to feed your brain, because your brain needs this backup system for glucose.